this is the climax of every COSM is Carver Mead. He's given speeches at least 20 of my cosmic conferences, microcosm conferences, telecosm conferences, and now COSM conferences, and he's truly the cosmic man. I met him after I was learning semiconductor electronics by writing the Rosen Electronics letter way back in the early 1980s, around 1981. And I went from one semiconductor company to another around Silicon Valley, and all of them had this volume on their desks or near their desks or in their bookcases of Carver's text on VLSI, VLSI logic and VLSI design, everyone in Silicon Valley felt they had to have this text, but I would ask them questions and they say, oh, it's the definitive work. But when I asked them what was in it, some of them knew, some of them didn't. But I felt I better read it. And soon I was meeting with Carver, and I learned that I wasn't a futurist. Carver was the real futurist. And his book on VLSI, which essentially expounded the basis for the foundry model that now completely prevails in global electronics, with TSMC being the major example. And as a matter of fact, Carver primed all leading figures in Taiwan about the benefits of the foundry model long before, just before Morris Chang went to Taiwan from Texas Instruments and started TSMC. So this is really a great vindication. Carver believed that if chip designers all had to have massive fabs entailing huge investments, the whole semiconductor industry would be stultified. If certain companies focused on foundries and designers focused on designing chips, you could have an efflorescence of chip designs all around the world, and the foundries would launch on Moore's Law. And Moore's Law, that probably Carver is most famous for both doing the research for Gordon Moore, and actually naming Moore's Law after Gordon Moore. And this was a pivotal moment really in our history. Moore's Law and its propagation has really informed the entire semiconductor industry ever since. Carver also advised Moore and advised Intel to launch a foundry itself, but they didn't get around to that until last year. Now Gelsinger has adopted the foundry idea. But I could go on and on about Carver. I've written biographies of Carver. He's in Microcosm, Telecosm, the Silicon Eye, all these, and I got about 100,000 words for a biography, which I won't read to you this evening. But Carver also has had a great vindication for his physical studies recently. He might tell you about that. But he also, in 1990, wrote a major paper for IEEE Journal on neuromorphic computing, and prophesied wafer-scale neural networks that could be the foundation for a vast expansion of computing. And it's just, I can't, this is a historic figure in the history of the industry, and we're so fortunate to have him here this evening.
Thanks, George. It's good to be at COSM again. We've heard just in the previous talk that there's a need to be able to train huge neural networks. And the only people that have enough compute to do that are the big companies. That sounds a lot like what it used to be like before foundries, where only the companies that had semiconductor fabs could innovate in silicon design. So here we are again. And so I want to talk about, you all know that what's called deep learning today is really training neural networks with the backpropagation algorithm. And so it's about 30 years ago when that was invented, and it had a long struggle before it became mainstream, which is only last 10 years or so. Part of what the COSM conference has always been about was and is information as an abstract notion and discussed in basically logical or mathematical terms, and information as a physical quantity. The thing about information is it can take on many forms, but it doesn't exist unless it's in a physical form, some physical form. Can be translated from one physical form to another, but unless it's embodied in a physical form, it doesn't exist. So it's this abstract, funny business. Computer scientists and many other fields get lost in the mathematics of the abstract stuff and don't think about the physical form that brings it to life. So if you look at training a neural network, what do? The basic operations are you have an input and you have somehow an answer that this input should generate. So you look at the answer you got from the network, and if it's different from the answer that's correct, then you correct the network. That's fine if you have a database where you have all the known right answers. That's an incredibly small fraction of data. So there's a better way to go about things if you want a lot of data. And it was mentioned today that the self-training network. I described an architecture for that in my 1990 paper, and it goes like this. You think of the network as a model. You put in inputs, and what the model does is predict what the next input will be. it turns out many problems, a very large set of problems, can be put in that form. We heard about that yesterday. Then the model, the neural network, puts out an output, which is a prediction of what the next input will be. Well, then you compare the next input with the prediction, and if they're the same, you don't do anything. If they're different, you correct the network by a backpropagation algorithm, and you put out an output to the next level. So you've done a wonderful thing. You've not only trained the network to be a better model for the stream of data coming through, but you've purified it so that the output of the model only tells you when something's interesting to the next level. Because if you've predicted it already, you have that information captured in that level of the network. And so you don't need to pass it on to the next network. This is what a lot of the brain does. And so how would you go about doing this if you weren't just simulating it on a computer? Well, what's in the computer that's useful for doing this kind of thing? What we do in the computer is we make transistors, and we wire them up into little circuits, and we decide ahead of time that our data are represented by ones and zeros. They're a binary representation because we have good logic for that. And then we build up painfully operations out of little circuits that do an AND or a NOR. And we wire all those up together to do simple things like adding. It takes a lot of transistors to do an add. It takes a number of bits to represent a value. Well, what does the network have? The network has values for the inputs. Those values go to a layer of neurons. Each neuron takes each of the inputs, multiplies it by a weight, adds all those together, subjects the sum to a nonlinear function, and then uses that as an output. There's nothing digital about a neural network. Those are all analog values. In today's world, they're simulated with lots of transistors that are either 0 or a 1. And every step of the computation, the values are restored because that makes it digital. Vast amount of the power that's eating up the cost of computing that goes into training neural networks is just restoring those 1-bit circuits. So what would you do if you were going to make a network that does what it says when you describe the network? You would represent the values as voltages. You would put the weight as a charge on a floating silicon gate. You would increment or decrement that charge with known very low power, very energy efficient ways to add charge or take charge off of floating gates. Been known now for 20 years. And the transistor that has a floating gate generates the nonlinear function that becomes a current, which is the output of that particular neuron. This kind of computation has a lot of advantages. In the first place, it takes vastly fewer transistors. It takes about 10,000 times less power. It has the property that if there are defects in the silicon, it means one of the inputs is stuck, which means that it isn't changing, so it carries no information, so the learning process learns to ignore it. So this kind of architecture is inherently defect and error tolerant. A architecture like this can be put on a full silicon wafer like we saw today, but you wouldn't need the water cooling. And that whole big suitcase-sized thing behind the thin little silicon wafer. So there's an opportunity there from looking at the actual function that is required in the training of a neural network and implementing it directly in the physics that's there on the silicon already. There's a big opportunity there. It's a factor of probably 1,000 at the system level. It's an opportunity that can be done today. That proposal was in my 1990 paper. There's something about the world, not just the US, that has an allergy to things that they've been told is bad. Everybody's been told that digital took over from analog because if you have analog, the errors all add up and finally you lose the signal. Learning systems learn one layer of the neural network, which is just a finite sum, and they restore the output of the neuron through the nonlinear function. So they're inherently restorative in layers. It seems like a perfect opportunity to actually make a low power, highly scalable engine for deep learning. It's an example of using the functions that are natural in the silicon to compute a useful overall function. It's an opportunity. I've been amazed at the reluctance of even technical people, but particularly financial and government people, to embrace an opportunity of this kind. Maybe somebody here will do it. This has been a great conference. Good to see you.